Yeah, our speaker this evening is a distinguished student of our former sadly deceased colleague, Mr. Marco. Having done his PhD there, he started actually his PhD. He's going to talk about this evening. So he's an electrified gentleman who is very excited about using electricity as a means of catalyzing chemical reactions. Seems like a very green way to do things, especially since electricity is cheap as peanuts these days. No?
Well, it depends on where.
Anyway, having done his degree in Louvain-la-Neuve, you then went to Vermont. And from Vermont, you decided to go, as one does, to Kazakhstan. I shall not dwell on that chapter of your career, which is obviously interesting, but you accepted a position of assistant professor in the university in Kazakhstan, and then developed a research program there, and then you came back to the absolute centre of the universe, which I believe is called Greenwich. At least for some people it's the centre of the universe. I'm not sure that some other people would agree. Never mind. Anyway, you are now at Greenwich, where you are, I've got the title correct, so I must actually read this. Full Professor of Synthetic Electrochemistry. That sounds very distinguished. That's good. I'm glad you've got a full professorship, because they're not as easy to find as they were in my day. Never mind. We look forward to hearing all about your chemistry, which has potential, and I hand the floor over to you and look forward to your talk. Kevin, thank you very much.
Well, thank you very much, Bob, for the invitation. Thank you, all of you, to be here tonight. So this is kind of a tricky lecture, because usually I only talk to organic chemists. It's not that I don't like other chemists, but so I made what I called an experimental lecture. Okay, I've never given it before. So basically, it's quite interesting with electrochemistry, because everyone is going to think about batteries and weird things like that. But let's go back to something that we all know at the moment, is that we are all trying to do what I call the electric revolution, maybe not. But you know, we all have polluting cars. We all might have that views in our minds, at least the public had that view in their mind that, you know, chemical industry is that thing that smokes a bit everywhere. But now we're moving to that, okay? So can we do the same with the manufacturing of our chemicals? And let's move to that. Can we actually start making molecules by using electricity and replace toxic chemicals? So this is obviously not new, but can we push it to the next stage where we actually can go even, probably in a few years, to production? So what I do in my lab is to develop organic reactions that are actually replacing expensive and toxic chemicals by simple electricity. We do also a little bit of other things like recycling of CO2, we do mechanistic studies, and we do what I call medicinal electrosynthesis. I always joke, this is literally every single thing you should not be doing in one project. Using electrosynthesis to make molecules, half of the world will tell you, not a great idea. Making drugs that have a metal in it, maybe not a great idea. Making drugs that have CO bonds in them, even worse. Injecting them in mice and then drawing blood and then going to a cyclotron to detect them. But anyway, that's another story. Let's focus on what we're here today for, directly here. A lot of people in the industries and, you know, in young PhD students studying organic chemistry are obsessed with medicinal chemistry. But this is a review and not by me. But if you look at the number of different reactions that a medicinal chemist will do to invent your future drugs, it's a tiny number of them. For 32% of their time, a medicinal chemist will be making peptides or amide bonds. Big deal. Then they will be a little bit more adventurous and start to do Suzuki-Miura cross-coupling. Okay, not still very exciting. They will do amination of aromatic cycles. Okay, still not super exciting. And the rest of the time is just going to be protection, deprotection. So literally, if you want to be a medicinal chemist, you don't really need a lot of toolkits. But does that mean that we have to stop there? Of course not. There are new methods, really, nowadays in synthetic chemistry, and I think I'm going to hopefully convince you that we kind of maybe start, we could switch our minds toward new reactivities. So why people should actually, I wouldn't say invest, but think at least about using electrosynthesis. First, it's kind of one of the greenest and safest technology that exists to perform transformation. I'm going to focus on reactions that are unique to electrosynthesis and probably very difficult to do in normal flask. It's quite cheap. You can see here, it's probably one of the cheapest source of electrons in the world. It's probably the cheapest reagent you could use. And it's also going to focus on the fact that it's extremely practical. And I'll come back to that. So how do we do that? Because it's all good to have ideas and words, but how practically do you do that? So here you have one of Michael Faraday's original setup, and you see that you have a battery here, and that's plugged to two electrodes that are into a solution. And you might think, this is probably like what? A few hundred years ago, and you're like, surely nowadays we have something better than that. Not really, we just make it look better, but the technology is exactly the same. So here you have combined basically a stir plate with a potential stat, but it's nothing else than two electrodes dipping into a solution. And you can put blue ink just for the fun of it, I guess. That's it. It's still the exact same setup. It's also something that probably most of you are doing every night. You are recharging your battery, and that's an electrolysis, mostly for an organic compound. But can we do that with organic material? Well, let's see. The problem when you talk about electrochemistry to people is that you get all these ideas, okay, depending who you are in the audience. But really what it looks like in real life is that, okay? It's not as glamorous as, that video or going to conference. It's a bit messy with wires everywhere, but again, tonight I'm going to be a bit like the restaurant. I'm going to serve you the dishes, and I'm not going to talk too much about, what's going on in the kitchen. But again, there is another, I would say problem, but another reason why people do not get into the field. They would claim that, look, this is really a field that I'm not confident about because I might have a PhD or at least some knowledge of organic synthesis, but I do not have any knowledge of electrochemistry. I don't know what works there. A lot of people are doing spectroscopy, including an MR spectroscopy, but they don't have a PhD in spectroscopy. So really the take-home message is that type of chemistry is a bit like driving a car. You can drive a car without knowing how to build a car, and that's really the take-home message. There are also two interesting types of chemists in this world. They are my colleagues that are going to be here. These are the perfect chemists in this world. You want a specific transformation, they will come with the most beautiful, complex catalyst ever. And they have very fancy labs that looks like that, because everything is air sensitive. And then there is us. That. This is the philosophy. If it's, too long, too delicate, we're not going to do it. So everything I'm going to show to you today is actually done under air. So none of the reactions that I will show you are really sensitive to air. None of the reactions that we are doing are sensitive to water. We're going to skip the salt, because normally whenever you do an electrolysis you have to add a salt to make your solution conductive, but that's kind of a waste because it doesn't do much for the reaction. And we want also to make things scalable, because if all you can do is 5 milligrams, or all you can make is 5 milligrams in a flask, it's okay, but how are you going to save the world with that? So, is it a thing? And here I have plotted the number of articles per year that are talking about organic electrochemistry. And you see that it's kind of flat, basically like, I started my career really around that time. And I was really, really happy because no one cared about what I was doing. And about 2016, I got a massive number of new competitors on the market, which freaked me out, but okay. And it's an interesting thing. It's still growing. I don't know if we're going to drop, but as you will quickly see, I don't really care if I'm trendy or not. Just doing that because it's interesting. What I'm going to stress really is that it's not a new discipline, okay? I have not invented anything. In the UK, you had people actually at Southampton, Richard Brown and Derek Pletcher, that we're doing electrosynthesis before, I think, anyone really, and then you have other players here. So it's not a new discipline at all, okay? This is what I call the new old chemistry. But really, Michael Faraday was the first one to actually publish the first organic transformation using electricity. And I will come back to that in a few seconds. And this is where I think electrochemistry will win. This is an interesting disconnection. If you want to make that molecule, you can see that there's a symmetry, okay? And what I suggest is to cut a carbon-carbon bond. And one of the first few things you learn in your organic classes is that that disconnection is certainly not what you should be doing, because it makes no sense. We all know that making sp3, or these naked carbon bonds, is something very challenging, and you should probably not be doing it. You should probably disconnect somewhere else. Okay, but what's the fun if you don't do something that you've been told not to do? What if it's coming from a natural product, that acid? What if we push the system further, and I say to you, I'm going to cut these 3 bonds here, and this is where, if you show that to your first year organic chemistry class, you will fail. But again, it's because, including myself, we've learned the same rules over and over, but maybe we have new tools nowadays. So what if this is coming from a radical cyclization that would be actually starting with the decarboxylation here, and we're going to do something that is quite weird and not common in organic synthesis. We can generate free radicals that can be combined with molecules. And although that might seem crazy, that was described in 1800s. This is called the Kolbe electrolysis, where you take 2 carboxylic acid and eventually you can carboxylate them in an electrochemical cell and they will bind together, losing the CO2. So when I started my career, I decided to look at that thing, because carboxylic acids are cheap, they're stable, and they are the perfect feedstock to generate these carboxyl radicals that very quickly lose CO2 and lead to the formation of the alkyl radical. Of course, everything started with Michael Faraday. In 1800 something, he reported in that original paper that whenever he tried to measure the conductivity of a solution of sodium acetate, he measured, or his measurements were not stable because a gas was involved. And this is probably a very typical problem with physicists. He did not care about the nature of the gas, so he just said, this is annoying, I don't like it. And you have to wait about 20 years where a German guy named Hermann Kolb discovered that this is actually ethane. And this is a picolar transformation. How do you go from 2 moles or molecules of acetate into that compound? And this is again where electrochemistry is kind of interesting compared to normal chemistry, because the first thing that will happen is that your anion here is attracted by your positive anode. It then gets oxidized, you remove an electron, you generate that carboxyl radical, which is completely unstable, very quickly lose a molecule of CO2, and you generate an alkyl radical. Now, what matters with electrochemistry is that what happens next to my electrodes. I generally do not care much about what happened in the bulk of the solution, so I can now trick my system and say, look, you're going to generate another radical from another acid. And eventually in space, they're going to be located very close to each other, they will recombine. And that's it. I've made my carbon-carbon bond in one step. So, for the rest of this talk, I'm going to try to focus on real-life example, also known as the industry is knocking on my door and saying, can you make that? And the answer inside me is like, probably not, but I kind of need the funding, so I say yes. This is actually a UCB project that we did in Belgium, also with Isvan before he actually unfortunately passed away, and I kind of helped with the rest of it. They are interested into making these this amide, this lactane here. And we thought, okay, can we take that very easily made and cheap starting material, use electrochemistry to generate a new radical here that then ring close, and then we use a coacid to form the last bond. They're quite useful product because the racemates, okay, some of them are used as smart drug, probably very good for students. They're supposedly making nootropic compound that help you to focus on things, to learn faster, better. No one really knows if they work, but as the industry would say, who cares, because they sell. But more interestingly, you have a family of racetams, and racetams are all anti-epileptics, or most of them are anti-epileptics. And anyway, long story short, we made these compounds. I will show you several of these slides over the evening. Don't worry, I'm not going to go through all these results. Basically, all you have to get is that it's working. So UCB is happy. We made these drugs, and then of course, as the pharmaceutical industry comes, they say, okay, you made 100 milligrams of these things. Can you scale it up? And usually, the answer is maybe. So scaling up electrosynthesis is not always straightforward, because the normal way would be making a gigantic electrochemical cell. Not always an easy idea, to be honest. Sometimes it works, sometimes it leads to a disaster, nothing works anymore. But nowadays we have an easy method which is called actually flow electrosynthesis. And the principle, and that has been done actually here in Belgium, is you get that thing here, which is a flow cell. So in a normal batch cell, you have two electrodes pointing, straight into the solution. In a flow cell, you tilt them by 90 degrees angle, like that, and you flow your reaction between the two electrodes, so you have a continuous manufacturing or continuous electrolysis, for instance. So again, we have UCB to develop that mini process. It's a little bit better, we get a better yield than what they got with the normal process here, and less solvent. They were kind of happy. So I was quite pleased with that small success. And then things started to be interesting. We looked at the formation of these compounds here. They're all precursor of very well-known drugs. You find this motif into them. And here, really, the thing is not about the chemistry itself, it's about how that happened. That reaction, which is the oxidation of the cyclobutanol, is the favorite one of a chemist at Imperial College called Phil Parson. So Phil Parson is 70 years old, and that's Phil Parson, as you can see. And that's literally a very old school chemist who called me with, a mask number on my cell phone, so I always freak out when I see this. And he said, "Oh, Kevin, I've got a great idea. Can we work together?" And I'm like, okay. So working together, we developed that reaction here, where we developed an electrochemical oxidation of these cyclobutanols to get to these drug precursors. It also happens that Phil Parsons do not have any fear, or maybe Health Safety did save him. This is a guy who, for his 70 years old birthday party at Imperial College, decided it was the right time to actually show us how to burn white phosphorus. I'm going to tell you, the first row of the audience literally stood up and backed away from that. That's the kind of man he is. But, still alive, it's all good. I'm going to skip the mechanism because it doesn't matter. But then eventually we made all these core molecules that could all be precursor to some drugs. Now, I'm a little bit like Phil Parson. I'm getting very excited about chemistry, and then sometimes I think this is not a great idea to make these molecules, but hey. So highly reactive intermediates, that sounds quite interesting and exciting. They are these types of molecules that you probably all have heard of, but never used. And I always say there are basically two reasons why you would not use a well-known molecule. The first one is that you can make them, yes, it's going to take a poor PhD student 7, 9 more days to make it. The yield is going to be ridiculous, and yeah, you could use it, but it's so impractical that no one wants to use it. The other good reason not to be making a molecule is that it ends up like that. Yes, you can make them, but you might not be there anymore to tell anyone about it. So yes, but they're still very useful, and I'll come back to that. And I think electrochemistry might give you some shortcut or safer way to actually make them. So we're going to start with the first one, where if you look at what I'm doing, I'm not such a creative chemist, to be honest. I'm taking the same thing, but instead of making radicals, I'm going to we want the molecule to be oxidized and get out of the system to be safe. But of course, the first flow system that I've shown you is a UCB flow system. UCB has money. As an academic, I had no money. So I said, okay, this is really a modern way of begging. I actually used Twitter, social media. I said, okay, I've got an idea. Could anyone print a small item in Teflon? It's a bit of a lie because I wasn't going to tell people, like, could you print me a whole flow system? Then my colleague Adrian Dove said, why don't you ask my friend Steve Hilton at UC London? Steve Hilton really foolishly said, okay. So I've learned how to do 3D printing for chemistry. I knew nothing about it, but I'm very naive, so I said, yeah, sure, let's do it. So here is the MacGyver thing we did with him. We 3D printed a flow cell. It's just a sandwich of 2 electrodes, and in between the electrodes you have a flow path where your liquid is just going, to go on the electrode like that, get electrolyzed, so it gets into a port here, gets through the flow cell, gets out at the end. But if you think about it also, what costs a lot of money in a flow system is not only the electrochemical cell, but it's the pump. So I said, okay, let's replace the pump. Oh yeah, crocodile. We replace the pump. This is also an entirely 3D printed system where we now have a simple bottle here with some solvent or your reagent. We put compressed gas, the one you want, air, argon, nitrogen. By increasing the pressure in the bottle, we push the liquid out on the tubing. That comes out. There's a pressure regulator here. It goes down, and you push it to flow through your cell, and then eventually you collect this thing on the other side. Now, because I wasn't very rich either, I got or kind of stole a power supply from our biochemist neighbor, and it's okay if you run quickly, you can get it, and plugged it here for the system. So this is really the cheapest flow system you can do. Of course, later we design it in a little bit more fancier way so that it fits commercial equipment, but this is the same principle. So that was our little adventure in the flow world. Of course, we flown few of our compounds through the cell. We managed to get the product out, all good. And take home message, all the yields in flow, or that for compounds that were alright in batch, are almost the same. The only one really striking is that compound that would get over-oxidized in batch is now totally fine in flow. So really, the flow technology is great, but it's not always a solution for everything. It has to be used when it makes sense. Then, because really I don't like to be too trendy, I looked at things that no one really cares about, orthoesters. Again, I'm not going to get into the nitty-gritty details here, but auto-esters are fantastic. You somehow going to manage to put 4 big oxygen atoms in one single little carbon. And they can do a lot of interesting chemistry. But again, I'm not interested too much about what you can do with them, but how can we make them so that people actually use them? And you see that the original synthesis relies on the hydrolysis of nitrile using either HCl gas or HCN gas if you're very brave, and gives you basically very mediocre yields of the desired autoester. So we thought, okay, can we start with the derivatives here, which is very stable, does not stink, although you see that there are 2 sulfur. It's usually heavy enough to be odorless. And here we go. We can actually electrolyze that in any alcohol we want and get very, very good yield in the corresponding autoester. Advantages are no drying, no degassing of the solution, and also no purification. If you do an extraction, basic extraction of this reaction, you do get the pure autoester. I always joke, but this is very close to the truth. This is a mix in your cell, you turn the current on, you go get a cup of coffee, you come back, you have your product. So usually PhD students are quite happy with that. It works with other alcohols. I'm not going to get into these details either. But it's also very good if you want to condense them with amino partners here. You do not have to isolate them if you don't want to isolate them. You can engage it in the next reaction by adding a nucleophile, and you get access to what Medchem likes, these benzoxazole, diazo, etc., benzimidazoles, which are Medchem motif that are quite interesting. You can also do a palladium cross-coupling on them just to show you how robust the method is. It works. We then got a request from the pharma industry, and probably because they started to trust me with electricity. They said, okay, can you help us to develop reactions where we actually add a nucleophile in alpha of these heterocycles? They never told me why, but the real reason is that they probably wanted to build libraries of biocompounds to test. So here we did something which was very displeasing to my students, because I said after working with sulfur, they complained a lot about the smell, making these precursors does smell. The precursors are fine, but I said, okay, let's work with something that does not smell, cyanide. And they're like, well, okay. So cyanation in this alpha position is quite interesting for medicinal chemistry. It is unfortunately not easy. Here we use kind of an easy to handle source of cyanide, tetrabutyl ammonium cyanide. If you know what you're doing, it's not more dangerous than anything else. Just don't lick your finger after it, but make sure that you know what you're doing. But at least it's not volatile, and it's safe to handle. Again, you have to pay attention, but it's not more difficult to handle than anything else. And we developed an electrochemical reaction that in one step is going to add a cyanide on these indoles. Now indoles are an interesting motif, again in medicinal chemistry. And I'm not going to bore you with the small details here. What I want to show you is that indoles normally are known to be really good at getting oxidized. If you buy indoles, they come, usually it's a black liquid because they have already been oxidized by oxygen. And usually when you do chemistry of indoles, you have to protect that nitrogen with something. When we decided, let's be crazy, let's try to put a cyanide onto unprotected indoles. It works. Yields are not great, but keep in mind this is a one-step reaction. And in medicinal chemistry, when people want to discover new molecules, as they told me, there are only two types of yields, enough and not enough. So 20% in one step, it's enough. Let's move on. We did it on other ring here, and really to show you that the system works, we tried on natural products. So we really started with products that have quite a few functional groups and are known to be tricky to functionalize. We did it, and we were able to actually add quite cleanly a nitrile cyanide in this condition. And here we are. I thought this is great, but let's try to make the system even more challenging. Making cyanide, we know how to make them. That is a bit more complicated, that's fine. Let's not make the obvious. Let's make, this is actually Alice in Wonderland. Always take that picture so that in case there's Disney around, I don't get sued. We tried that. Can you make these weird compounds? We're literally going to reverse the bonding. Okay. Isocyanide. I usually keep asking the audience, has anyone ever handled an isocyanide in their life? Usually you would remember. Isocyanides are defined by Wikipedia as non-lethal weapons. The smell of an isocyanide is, I would describe it as rotten flesh with a hint of metal. So basically, this is great. If your synthesis of isocyanide works, you will know it very quickly. Probably the whole lab will know it very quickly. And if for like us you work for months on it, the whole building will hate you to some extent. Again, they're very useful for a lot of chemistry. They're not easy to make. The way to make it is by dehydration of formamide. Formamide are not super stable. OPCO3 on small scale is fine. On grand scale it starts to be a little bit trickier to use and it's not super clean. So we thought, okay, can we actually electrolyze these aminotetrazoles? They are very easy to make. From the aminotetrazole here, you can buy kilos for nothing. I have no clue why. Is it so cheap? It's a byproduct of a process somewhere. You make them, and eventually when you oxidize them, you form what is called a full Wien-type structure that loses very quickly 2 molecules of nitrogen, and that gets you to your isocyanide. So okay, we made isocyanide. So we made all of that. I think by the end, so one of my friends said that his one of my PhD students said that his roommate didn't want him to keep doing chemistry, but we made them, okay? And most of these things could have very, very hardly been made through other methods, especially the one that has an amide here. We made them in flow also to show that you can actually make it on a larger scale if you want to. It's very clean. You can decide not to isolate them because they're quite stinky, to be honest, and engage them in the next step in coupling. It's fine. Then we move to the next iso compound, which is the isocyanate. Again, not a great compound to use. You find these isocyanate everywhere. Polyurethanes, you know, your polymer. It's a polymer of urethanes. Oh, sorry, that one, not that one, that I made to that way. They are very useful, but very highly problematic. The easiest way to make them is by using phosgene. Not great, okay? They're also extremely toxic because they bind to your DNA, so not great. If you have to isolate them, it starts to be quite dangerous. So okay, we thought, can we help here? We decided to make these amino carbamic acids. Again, they're completely stable, very easy to make. And we said, let's electrolyze them, and much to my surprise, we actually did get what I planned, an isocyanate. Again, long story short, you do not have to isolate them. You can add an amine directly after electrolysis, you get ureas. You can add an alcohol or a thio, and you get carbamate and thiocarbamate. No need to isolate these things. We did it in flow. At this point of my life, you can guess that I made a little bit of money because I was able to buy 2 professional flow systems for electrosynthesis. And again, we made them by flow, and it's working. I mean, more or less. The yields are not fantastic, but proof of concept, you can make them on larger scale if you want to. And finally, to finish the iso series, we decided, can we make the isothiocyanate? Again, not going to get into details. These compounds are very good building blocks, but again, look how to make them. It's quite complicated, and really the take-home message or the motto of my lab is be lazy, be simple. Can we make that from basically an amine and CS2? And yes, you can do that. The amine will condense on CS2, and then if you oxidize that electrochemically, you end up with the isothiocyanate. Again, you're going to ask me probably where the second S has gone, and the answer is you can ask me, but I have no clue. Don't know. Gone. I'm not the only one to be clueless. A lot of other people have actually looked at that and no clue. So we made them. Okay, I'm not going to go through the details here. We made them. It's fine. And just a few slides before I finish, I promise. Stay with me. This is where things are getting excited. We made explosives. Not really. Okay. It's half of the story. Diazo compounds, fantastic compounds. Lot of chemistry with them. Problem, they tend to explode when you heat them up. So okay, we made an electrochemical method by oxidation of hydrazone. Alright. We had to use a little bit of an iodine as a catalyst, but we made diazo. Now we very proudly say, guys, we made diazo without heating or using very toxic reagent. But we lied like 99.9% of the authors in the literature. We made stabilized diazo. So all these compounds here are stable. Of course, do not heat them up. They are stable enough to be isolated. You can put them on a column to purify them. You can do extraction. You can see them. We're now working on unstabilized diazo. This is a bit more tricky and dangerous, but we are eventually going to get there, I'm sure. Then my student really also wanted to do something trendy, fluorination. And again, without getting into the background of fluorination, because there are much, you can invite someone that will make an entire fluorination talk. Most of the fluorination methods here are relying on HF, KF, crown ether. That's expensive. HF, if you have never used it, I do not recommend. This is etching the glass, so you have to use Teflonware to do that. And here we decided, why don't we just do the obvious? use something that everyone has in their lab, a BF4 anion. And the idea is we generate from an acid, my beloved acid, a carbocation that is able to extract a fluoride from a very simple, completely stable, I would say almost non-toxic salt, and you get the fluorination. Again, it works, we made fluorine compound. Yields are not great, but again, I think the idea here is not to get the best yields, is to get to your compound in a very quick and safe way. We scale it up, it's fine, I'm not going to go through that in details. Yes, let me finish with that. This is probably the most crazy thing we ever done. We all have learned in first year organic chemistry that you can add hydrogen gas on a double bond. And it's true. You just have to use a catalyst, palladium, platinum. But can you do it without having to use hydrogen? So electrochemists said, yes, we can do it. It's been like 100 years we've done it. But hey, they tricked the system by adding an electron withdrawing group, so of course you can do it. But that was, flipping through the old literature. And there's a very interesting reagent here called diamide. Diamide is magic. It will do hydrogenation at room temperature of double bonds. But why is no one using it if it's so good? The first reason is that the reaction with a double bond and diamide is extremely slow. And what it does most of the time is react with itself to generate nitrogen and hydrogen back. Not great, so you have to use a large excess. So here I come. I say, no, we can use electrochemistry. So I'm not going to go through the mechanism here, but look what we managed to do. We managed to actually do hydrogenation of double bonds simply by mixing things in methanol with a little bit of hydrazine. We can now reduce almost any types of double bonds. We can actually be more selective than hydrogen and palladium. We can reduce double bonds in presence of carbon iodine bond. This is very difficult to do with palladium. We can reduce terminal double bonds in presence of internal double bonds. Again, it's not obvious to do that with palladium. Okay, can we do other things? Of course, internal double bonds are fine. We can move also to alkyne, triple bonds, no problem, we can reduce them. We can reduce nitro compound and azide, no problem. Again, no hydrogen involved at all, it's extremely easy. And then, the cherry on the cake. What happens if I add D2O in my system? A very cheap source of deuterium. Well, we can now do deuteration. These would normally require to use D2 gas to do that. It's very difficult to get your hands on D2 gas, and you have to be very rich to do that. So we could replace it with our method. And just to leave you on a few things to think of, and to show you that I think about the real life application, we are now in a multi-partner project where we are looking at fuel cell and how to make green hydrogen. Of course, I'm an organic chemist. Green hydrogen is not really my field. Now let that to my inorganic colleague, and you see that complex catalysts and things like that. But they asked me on the other side of the hydrogen machine, can we make something that is high value added? An organic reaction. So you might think this is going to be a tiny cell in the lab. But when you talk, I always joke to Finnish people, when they mean business, they mean business. So in Finland, they are building an entire factory to make that happen. And they did beg me, please do not do the isocyanide reactions, because we might not survive with the smell. It's actually made on 16,000 square meters electrons. Finally, just to let you know where we're located. We're located here in the southeast of UK, and of course in Greenwich. We have 3 campuses. You all have seen the campus in various movies. I joked this morning, but my parking space is behind that thing here. So basically, I never ever have it free. And yeah, we do welcome students at every level, including, we do have high school students from Belgium coming for a few weeks. We have a lab dinosaur. This is Halloween. I don't know if they do that in Belgium. I was half pleased when one of my French students came as a dinosaur in the lab to use a golf box. But who am I to say that? But yeah, and these are actually the people in the group that are doing the work. And I always joke, but this is true. The only way, this is a crap picture, let's be honest. because the only way I managed to get them all at the same time and the same place is by, for students buying free food. So what you see, that's still smiling, so things might be alright. But again, thank you again for your invitation, and if you have any questions, I might try to answer.
Thank you very much, Kevin. I recognise a few names up there. I haven't seen Clotilda for a long time.
Oh, you know her?
Oh, very well. Yes, she was a student on one of our advanced courses in
very busy.
She's very good. Very good. Questions? Ladies and gentlemen. Yes.
I noticed on your various slides, different syntheses, a number of different electrode materials. How important is the
everyone asks me that. The real answer is that it's definitely important. And there are two schools here. I have colleagues that are going to screen hundreds of different electrodes and tell you that the best one for that reaction would be an alloy that you can only find at the basement of someone in the Netherlands. Which is great, but you're never going to do the reaction if I tell you that this is where you have to source your electrodes. Our approach is a bit more simpler. We just decide to use the standard box electrode, platinum. It's expensive, but again, usually you can keep it for your whole lifetime. Carbon graphite, because it's very cheap. And then sometimes we look also at stainless steel and nickel, and we really stop there. Because basically, most of the reactions will always work, depending, it doesn't matter which electrode you use, the yield might be different. But my point of view on that thing is, if you can get 50% of what you want with what you have in the lab, you will do it rather than source a very expensive electrode to get 90%.
Well, question.
I've got another question about electrodes. There's on one of your syntheses, you have a synthesis where it had two different materials. I think it was nickel.
Yes.
What's the reasoning for
that? It's carbon graphite. So it's a very good question. So, because I'm an organic chemist and an academic chemist, I literally waste half of my reaction in my cell. One of the two electrodes, I don't care what happens. I just want something that is not going to be problematic. So on my cathodes, I always produce hydrogen. And it happens that in all these reactions, there are always acids, or there's always a proton lying around that can be reduced. And when you use nickel, platinum, or stainless steel, the amount of energy you need to put is really minimal to make hydrogen. So that's, if you want, that blocks my cathodic reaction, and that sets it to the reduction of proton into hydrogen, which doesn't do any or harm to my other reaction. So a bit of a trick here.
Do you consider green chemistry to be very important?
I think green chemistry. I think green chemistry. I've said it at the UPAC. I think green chemistry is important, but a lot of people claim that they're doing green chemistry. But as soon as you use a solvent to do your extraction, you're not green anymore. And very rightfully, when I think it was in Green Chemistry, the RSC journal, someone said if you have to purify your compound, that's it, it's not green anymore because you use solvent, you use silica, you use everything. So I think we do not have to be green yet. We just have to tend to be greener than what is now available. So I think green chemistry is definitely important. But I don't think there's any super green or completely green processes yet. It's probably greener options.
Well, I would have thought it was almost an impossibility, without going into mixed phase systems, to be able to do any kind of organic chemistry in totally aqueous.
No, but I do have colleagues that are doing what they call mechanochemistry, where they just make solids with no solvent. But again, if your compound at the end requires purification, it's probably better than with solvent. We can argue. It all depends on all the single steps for the whole process that you have to look at. I think it's challenging. So I would never claim that I'm doing anything like green chemistry. I just said I'm trying to be greener than the methods that are available.
No, I'm just intrigued by, because it's obviously become a big fad in chemistry. That the only proper green chemistry that goes on is biochemistry.
I'm not kidding. Biocatalysis is getting bigger and bigger in the industry nowadays.
Of course.
Yeah.
It's in fact, if we could reproduce something like photosystem 2
Oh,
just to convert water into protons, electrons, and oxygen, we would be way beyond the limits of the conceivable in terms of making free energy.
No, it's true, but also in terms of medicinal chemistry, recently the industry told me that nowadays the way to reduce a ketone is to use enzymes. It's not to use chemical reagents. They say this is the way we work.
It reminds me of a colleague in Massachusetts Institute of Technology who is a well-known enzymologist, but his letterhead is on his paper, on his writing paper, was enzyme chemistry, not different, just better. And I think that's what chemists are now beginning to waken up to, is that there's a lot of good. It's quite interesting because you talk about the reaction. We were talking earlier about the basic reactions that people need to know in organic synthesis. In fact, when I taught intermediary metabolism, I would start off with a 2-lecture series on the chemical reactions that you can find in biology, and there are only half a dozen of them at the most. And if you understand those, you can write the entire intermediate metabolism, starting with glycolysis of the Krebs cycle, without any problem, because it's completely chemically logical. But that's another story. Thank you once again. Do we have other questions? David?
Can you put a couple various reactions together so that you, without isolating the initial product?
Yes, we can. We have done it a few times. We tried telescoping things to have them back to back. It's possible. We have actually in the pipeline a few electrochemical things where, let's say you electrolyze a molecule, you generate one intermediate that can get further electrolyzed into something even more interesting. You could do it. And in flow chemistry, this is what flow expert, which I'm not, are doing. They put modules. They say first reaction, that module, the product goes into a second module, and they plug that. They do that, and they get amazing, very complex processes in one line, basically, with pumps everywhere, and it's fascinating to see how it works.
Well, thank you once again, and let me offer you a small reminder that we do make some things apart from beer in Belgium.
I know. I'm taking it before.
This is the one that you...
That's my favorite one.
And I have made sure that there are no alcoholic centres.
Thank you, I might survive.
It's strictly alcohol free. Thank you, Kevin, once again.
Thank you.
Well, thank you all for coming. It was a nice little natter and